You are not still. Nothing around you is still. The chair beneath you, the floor that holds it, the ground under the floor, the continent under the ground, all of it is in motion, and the motion does not stop at the edge of the world. The earth is turning. The earth is falling around the sun. The sun is sweeping through the galaxy at a speed that would carry you from one coast of a country to the other in the time it takes to draw a single, slow breath. And the galaxy itself is moving. And the cluster of galaxies that holds our galaxy is moving. And the supercluster that holds that cluster is moving. None of it is at rest. None of it has ever been at rest. For most of the long history of our species, we did not feel any of this, and we did not know it. The sky looked fixed. The stars seemed fastened to a dark ceiling that turned once each night and returned, season after season, to the same arrangement. It took centuries of patient watching to learn that the ceiling was not a ceiling, that the fixed points were suns, that the suns were drifting, and that we were drifting along with them. And then, far more recently, in the span of only a few decades, the measurement deepened into something stranger than drift. We learned that we are not simply wandering through space at random. We are being pulled. Our galaxy, and the galaxies near it, and the galaxies near those, across a region so wide that light itself needs hundreds of millions of years to cross it, are all moving together. Not scattered, not random, coordinated. All of them leaning in the same direction, toward the same quiet patch of sky, as though something out there was calling them home. We cannot see what they are moving toward. It sits behind the body of our own galaxy, screened by dust and crowded starlight, in a part of the sky that astronomers, with no apparent sense of irony, named the zone of avoidance. We only know the thing is there, because everything is falling toward it. We mapped its presence the way you might map a stone at the bottom of a dark pond, not by seeing the stone, but by watching the way the water bends around the place where it rests. Tonight, slowly, with no need to hurry and know where we have to be, we are going to follow the fall. We are going to begin with the small motions we can feel, and then the larger motions we cannot, and we are going to keep widening the frame until we arrive at the edge of what we know, and then a little past it, into the place where the knowing runs out and only the falling remains. Settle in, let your breathing slow. There is a long way to go, and the only thing required of you is to stay and to drift and to let the scale of it carry you down. Begin with something you can almost feel. You are sitting on a planet that is spinning. At the equator, the surface of the Earth turns at roughly 1,000 miles every hour. You do not feel it because everything around you turns at the same speed. The air, the oceans, the mountains, all of it moving together so smoothly and so steadily that the motion vanishes into stillness. This is the first lesson of everything that follows. Motion that is perfectly shared becomes invisible. You can only notice movement by comparing one thing against another. A still room tells you nothing. A reference point tells you everything. The spinning Earth is also falling. It is falling around the sun, held in a long, curved path by the sun's gravity, traveling along that path at about 18 miles every second. In the time it has taken to speak this sentence, you and the planet beneath you have moved farther than the distance between most cities. And again, you feel nothing, because the falling is shared. The whole Earth falls together, and so the fall becomes the ordinary background of life, the thing too constant to notice. The sun is not still either. The sun, with the Earth and all the other planets trailing behind it like a slow comet, is sweeping around the center of the Milky Way. The speed of that sweep is something close to 140 miles every second. It is so fast that the numbers stop meaning anything, and yet it is so vast a circle that a single trip around the galaxy takes more than 200 million years. The last time the sun was in the part of the galaxy it occupies tonight, there were no human beings, no apes, no creatures you would recognize. The dinosaurs had not yet reached their fullest spread across the continents. The sun has not completed even one full orbit since the age of the great reptiles. This is the rhythm of the galaxy. It does not keep our kind of time. So already, before we have left our own galaxy, you are layered in motion. You spin with the Earth. You orbit with the Earth around the sun. You sweep with the sun around the heart of the Milky Way. 3 motions, stacked one inside the other, and you feel none of them because each one is shared by everything around you. And these are only the beginning. These are the motions inside our own galaxy. The galaxy itself is also moving. And here is where the question begins to open. Moving relative to what? If everything inside the galaxy moves together, then how could anyone ever measure the motion of the galaxy as a whole? Against what stillness could it possibly be compared? This is the problem that astronomers had to solve before any of the rest of the story could be told. To measure the motion of the entire Milky Way, they needed something to measure it against. They needed a reference frame, a fixed backdrop, some standard of rest against which the wandering of whole galaxies could be read. And for a long time, it was not obvious that such a thing existed at all. The universe offered no painted wall, no marked ruler, no still point that everyone could agree was truly standing still. Every object they could see was itself in motion. To find the movement of the galaxy, they would have to find a way to stand outside it, and nothing lets you stand outside a galaxy. The first tool they reached for was light, and the way light changes when its source is moving. You already know a version of this effect from sound. When a vehicle with a siren approaches, the pitch of the siren rises, and as it passes and recedes, the pitch falls. The sound waves are bunched together as the source comes toward you, stretched apart as it moves away. Light behaves in a similar manner. When a source of light moves toward you, its waves are compressed, and the light shifts very slightly toward the blue end of the spectrum. When the source moves away, the waves are stretched and the light shifts toward the red. Astronomers learned to read these shifts with great precision, and in doing so, they gained a way to measure the motion of distant objects along the line of sight, toward us or away from us, written directly into the color of their light. When they turned this tool on the galaxies beyond our own, they found something that at first seemed to swallow every other motion. Nearly every galaxy was shifted toward the red. Nearly every galaxy was moving away. And the farther away a galaxy sat, the faster it was receding. This was the discovery that revealed the expansion of the universe itself. Space is not a fixed stage on which the galaxies move. Space is growing, stretching, carrying the galaxies apart from one another, the way raisins are carried apart in a rising loaf of bread. The galaxies are not so much flying through space as being carried along by the swelling of space between them. This expansion gave astronomers their first hint of a backdrop, but it also gave them a problem. The general outward flow, the great stretching that carries every distant galaxy away from every other, is so strong that it hides the smaller, more local motions underneath it. If you want to know whether a particular galaxy is doing something more than simply being carried outward by the expansion, you have to first subtract the expansion away. You have to know how fast a galaxy at that distance should be receding, purely from the stretching of space, and then see whether it is moving faster or slower than that and in what direction. The leftover motion, the part that cannot be explained by the expansion alone, is what astronomers call the peculiar velocity. It is the true motion of the galaxy through space, its own private drift, separated from the universal tide. Consider, for a moment, what it actually takes to know the distance to a single galaxy, because the whole enterprise rests upon it. You cannot stretch a measuring tape across millions of light years. You cannot bounce a signal off a galaxy and wait for the echo to return. The distances are far too great for any such directness. Instead, the astronomers rely on objects whose true brightness they believe they understand. If you know how bright a thing truly is, and you measure how bright it appears from where you stand, the difference between the two reveals how far away it must be, in the same way that a candle of known strength betrays its distance by how faint it has grown across a dark field. Certain stars pulse with a rhythm tied to their true brightness. Certain exploding stars flare to a peak that is nearly always the same. Whole galaxies, in certain ways, give away their true size or their true luminosity through the speed at which they spin. Each of these is a rung on a long ladder of distance, each rung calibrated against the one below it, the whole ladder climbing from the nearby stars out into the deep field of galaxies. And every rung carries its own small uncertainty, and the uncertainties accumulate as you climb, so that by the time you reach the far galaxies whose falls you wish to measure, the distance is known only within a margin, and that margin is the haze through which the astronomers must squint to read the faint, private motions buried beneath the great expansion. The word peculiar here does not mean strange, it means particular, belonging to that one object. The peculiar velocity is the personal motion of a galaxy, the part of its movement that is genuinely its own and not merely the shared drifting of expanding space. And it is in these peculiar velocities, these small private motions hidden beneath the overwhelming outward flow, that the real story is written. To find them, astronomers had to become extraordinarily careful. They had to measure the distance to a galaxy by one method, predict how fast the expansion alone should be pushing it away, measure how fast it was actually moving by the shift in its light, and then take the difference. The difference, often small, often buried in the uncertainty of the measurement, was the prize. The difference was the fall. But peculiar velocities, measured this way, are difficult and noisy. Distances to galaxies are notoriously hard to pin down. A small error in distance becomes a large error in the predicted expansion speed, which becomes a large error in the leftover motion. For the local motions of single galaxies, the method works only with great labor and great caution. What the astronomers needed to see the full pattern was something cleaner. They needed a single, steady, universal reference against which the motion of our own galaxy and our own local neighborhood could be read without ambiguity. And in the middle of the 20th century, almost by accident, that reference was found. It came from the earliest light in the universe. Long before there were galaxies, long before there were stars, the entire cosmos was a hot, dense, glowing fog. In that era, the universe was so hot that atoms could not hold together. Light could not travel freely. It scattered endlessly off the dense sea of particles, trapped, unable to move in a straight line, the way light is trapped inside the glowing interior of the sun. Then, as the universe expanded, it cooled. And at a certain moment, a few 100,000 years after the beginning, it cooled enough that the fog cleared. Atoms formed. The particles that had blocked the light settled into place, and the light, suddenly free, streamed outward in every direction, and it has been streaming ever since. That ancient light still fills the universe today. It has been traveling for nearly the entire age of the cosmos. Stretched by the long expansion of space across those billions of years, it has cooled from a blinding glow into a faint whisper of microwaves, a dim and almost perfectly even radiation that comes from every direction in the sky. Astronomers call it the cosmic microwave background. It is the oldest light there is, the leftover heat of the universe's first clear moment, and it surrounds us on all sides like the inner surface of an enormous ancient shell. When this faint radiation was first detected, it was not even recognized for what it was. It arrived as a persistent hiss, a low background noise that would not go away no matter how carefully the instrument was cleaned and checked, a whisper coming from every direction in the sky at once. Only gradually did it become clear that the hiss was not a fault in the equipment, but a signal from the dawn of time, the cooled and stretched remnant of the universe's first light, arriving from all sides because it fills all of space. There is something fitting in that. The oldest light in the cosmos announced itself first as a noise that could not be silenced, a steady glow with no single source, present everywhere the instrument was pointed. And precisely because it is everywhere, and precisely because it is so nearly the same in every direction, it became the one thing against which our own motion could finally be weighed. The faintest and most uniform thing in the universe turned out to be the ruler we had been missing all along, the still surface beneath all the restless drifting, the backdrop that the milling galaxies could never provide. And here is the gift that this ancient light gave us. It is almost perfectly the same in every direction. The early universe was extraordinarily smooth, extraordinarily uniform, and so the light that escaped from it carries that smoothness with it. Look one way, and the background glows at a certain faint temperature. Look the opposite way, and it glows at very nearly the same temperature. To an astonishing degree of precision, the oldest light in the universe is even, balanced, the same everywhere. And that evenness makes it the closest thing the universe offers to a fixed backdrop, a standard of rest, a still surface against which motion can finally be measured. Because if we are moving through this sea of ancient light, then we should see it shifted. In the direction we are traveling toward, the light should be very slightly compressed, very slightly warmer, and shift a hair toward the blue. In the direction we are leaving behind, it should be very slightly stretched, very slightly cooler, and shift a hair toward the red. Our motion through the oldest light in the universe should print itself onto that light as a pattern. One side faintly warmer, the opposite side faintly cooler, a smooth gradient across the whole sky. And, when astronomers built instruments sensitive enough to look, that is exactly what they found. The pattern is called the dipole. One half of the sky, in the ancient background light, is measurably warmer than the average. The opposite half is measurably cooler. The difference is tiny, a few thousandths of a degree, far too small for any eye to see, but the instruments saw it clearly, and the meaning was unmistakable. We are moving. Our entire local region is moving, as a whole, through the rest frame of the oldest light in the universe. And the direction of the warm side of the sky is the direction we are moving toward. The ancient light had become a compass. The smoothest thing in the cosmos had become the one surface against which our own deep motion could be read. When the astronomers worked out the speed implied by that faint warming and cooling, the numbers stopped them. After accounting for the spin of the Earth and the orbit around the Sun and the great sweep of the Sun around the galaxy, after subtracting away all the motions we already knew about, there was a motion left over that none of those could explain. Our galaxy, together with its small companion galaxies, the whole local group of galaxies that the Milky Way belongs to, is moving through the rest frame of the ancient light at something close to 600 kilometers every second, roughly 1,000,000 miles every hour. And that motion is not in some random direction scattered against the others. It points toward a particular region of the sky, low in the southern celestial hemisphere, toward the constellations of Centaurus and Hydra. Sit with that number for a moment, in the slow dark. 600 kilometers every second. The whole local group, the Milky Way and Andromeda, and the dozens of smaller galaxies bound up with them, all of it falling together in the same direction at more than 1,000,000 miles an hour toward one specific quarter of the sky. Not drifting, not coasting. Falling with a direction and a destination toward something we had not yet seen and could not yet name. The compass pointed. The only question left was what stood at the end of the line it drew. This was the moment the story changed. For a long time, astronomers had assumed that the local motions of galaxies were mostly small and mostly random, little tugs from this neighbor or that, more or less canceling out. The expectation was a kind of gentle disorder. Galaxies milling about, each pulled a little this way and a little that way by whatever happened to be nearby. What the ancient light revealed was something else entirely. The motion was not small. The motion was not random. It was large and it was coherent, and it had a direction. And a motion that large, shared across so many galaxies, pointing all one way, does not happen by accident. Something was pulling. The only question was what, and how much, and how far away. So the astronomers did the natural thing. They began to map the neighborhood. They began to measure the motions, not just of the local group as a whole, but of as many individual galaxies as they could reach, across as wide a region as their instruments would allow. They wanted to know whether the local group's fall was a local oddity, the Milky Way and its companions chasing some nearby clump, or whether it was part of something larger. They wanted to know how far the coordinated motion extended. They wanted to map the flow. The mapping was slow, painstaking work, carried out over years by many teams, in many countries, with many different instruments. Measuring the peculiar velocity of even a single distant galaxy is hard, as we have seen, because it requires knowing the distance with great precision. But the astronomers had developed methods. They had ways of estimating the true size or true brightness of certain kinds of galaxies, so that by comparing the true value to the apparent value they could read off the distance. From the distance and the observed shift in light, they could subtract the expansion and recover the peculiar velocity, the private fall, one galaxy at a time, then 10, then hundreds, then thousands. They built up a chart of the local motions of the universe, a map not of where the galaxies are, but of where they are going. It is worth lingering on how strange and how human that labor was. Picture the work of it, spread across observatories on several continents and across years that turned into decades. A galaxy is chosen. Its light is gathered, night after night, and split into its colors, and the shift of those colors measured with great care. Its distance is wrestled out of the long ladder of methods, each one checked against the others. The expected speed of pure expansion is calculated and subtracted away, and whatever small motion remains is recorded, a single faint arrow added to a growing chart. Then another galaxy, and another, each one a night's work or many nights' work, each one a small and uncertain measurement, none of them impressive on its own. No single galaxy's arrow proves anything. The motion of any one galaxy could be noise, could be error, could be the random tug of some unseen neighbor passing close. The pattern lives only in the gathering of thousands, in the way the individual uncertainties begin to cancel, and the shared direction begins to rise out of the scatter, the way a faint shape resolves out of a field of random dots once you have plotted enough of them. The flow was not discovered in a single night by a single instrument. It was assembled, slowly, out of a great accumulation of small and patient acts of measurement, until the direction hidden inside the noise could no longer be denied. And as the map filled in, a pattern emerged that was far larger and far more striking than anyone had expected. It was not just the local group that was falling toward Centaurus. The galaxies around the local group were falling that way too, and the galaxies around those. And the galaxies are hundreds of millions of light years off in the same general region of the sky. Across an enormous stretch of space, far larger than anyone had imagined could move together, galaxies in their hundreds of thousands were leaning in the same direction, drifting toward the same distant area of the sky, as if the whole region were tilted and everything in it were sliding down the same long slope. Think about the scale of what that means. We are not talking about a handful of nearby galaxies pulled toward a common clump. We are talking about a flow that spans a region on the order of 500 million light-years across. Within that vast volume, the galaxies are not moving every which way. They share a common drift. They have a preferred direction. Lay out the arrows of their motion, the way you might lay out the direction of the wind across a weather map, and the arrows do not point at random. They converge. Across 500 million light-years of space, the arrows lean inward toward a single region, like leaves on the surface of a slow river, all turning to follow the same hidden current. A current implies a source. Wind that blows in one direction across an entire landscape implies a vast difference in pressure somewhere beyond the horizon. And galaxies that fall in one direction across 500 million light-years imply a vast concentration of mass somewhere in the direction they are falling toward. Mass is the only thing that pulls like this. Gravity is the only force that reaches across such distances and bends the motion of whole galaxies. So the converging arrows were not just a curiosity, they were a measurement of something unseen. They were the bent water around the stone at the bottom of the dark pond. They told the astronomers that somewhere out toward Centaurus, hidden in the depths of space, there had to be an enormous accumulation of mass, a gravitational anchor great enough to draw an entire region of the universe toward itself. They gave it a name before they could see it. They called it the Great Attractor. The name was almost a confession. It described what the thing did, the attracting, the pulling, without describing what the thing was. It was a placeholder for an absence, a label hung on a region of the sky where the gravity was clearly enormous, but the cause was not yet visible. The Great Attractor was, at first, less an object than a conclusion. It was the answer to a question the data had forced upon them. If all these galaxies are falling this way, what are they falling toward? And the only honest answer, at the start, was a name and a direction and a rough idea of how far and almost nothing else. The rough distance, worked out from the speed of the flow and the way the motion changed across the region, placed the Great Attractor at something on the order of 150 to 250 million light-years away. Far, by any human measure, but not at the edge of the visible universe. Not impossibly remote. By cosmic standards, the Great Attractor sits in our own backyard, in the nearby universe, close enough that its pull on us is strong and direct, and that nearness only deepened the strangeness of the situation. Here was a gravitational engine powerful enough to move an entire region of galaxies, sitting at a distance that, on the scale of the cosmos, is right next door, and yet for a long time no one could see what it was. The thing was close, the thing was huge, and the thing was hidden. To understand why it was hidden, you have to understand where, in our sky, the Great Attractor lies. And to understand that, you have to remember the shape of the galaxy we live inside. The Milky Way is a flattened disk, a great spinning wheel of several 100 billion stars, with a bright bulge at the center and long spiral arms wound through the flat plane. We do not live above the disk, looking down on it from outside. We live inside it, embedded within the flat plane of stars, far out toward the edge, looking outward through the disk in every direction. When we look up at the band of light we call the Milky Way arching across a dark night sky, We are looking edge-on, along the plane of our own galaxy, into the thickest crowd of its stars and the densest curtains of its dust. That dust is the problem. Between the stars of the galaxy lie vast clouds of gas and fine dust, dark material strung through the disk in great lanes and sheets. These clouds are not dense by any ordinary measure. The space between the stars is emptier than the finest vacuum any laboratory can make. But the distances are so enormous that even the thinnest scattering of dust, accumulated across thousands of light years, adds up to an impenetrable haze. Look out of the galaxy in a direction that takes your line of sight up and out of the disk, away from the crowded plane, and the view is clear. You see straight out into the wider universe, galaxy after galaxy receding into the dark. But look out along the plane of the disk, through the thickest part of the crowd, and the dust closes in front of you like a fog, and the distant universe behind it vanishes from view. This obscured band, the strip of sky blocked by the dust and stars of our own galaxy, is what astronomers call the zone of avoidance. The name dates back more than a century, to the early days of galaxy mapping, when astronomers noticed that the galaxies they could see seemed to avoid a certain band of the sky. There was a strip running along the plane of the Milky Way where almost no galaxies appeared. It looked as though the galaxies were avoiding that part of the heavens, keeping their distance from it. But of course, the galaxies were not avoiding anything. The galaxies were there, behind the band, in their usual numbers. They were simply hidden, screened from view by the dust and the dense starlight of our own galaxy lying in the foreground. The zone of avoidance is not a region the galaxies avoid. It is a region we cannot see into. It is the blind spot of our own position, the shadow our galaxy casts across the sky. There is something almost poetic in the bare fact of the blind spot, and something humbling in it too. Of all the directions our region might have chosen to fall, of all the quarters of the sky toward which the great current might have run, it runs toward the one place our own home most thoroughly conceals. We are not neutral observers perched in clear and open space. We are buried in the disk of a galaxy, looking out through its crowded plane, and that plane lies across a fifth or so of the entire sky as a band of obscuration, thinning at its edges, all but impenetrable at its heart. For the early mappers of the heavens, who worked only in ordinary light, this band was simply a place where the galaxies stopped, an empty lane running across the sky, and they could only guess at what lay behind it. They could not know that the most important structure in our local universe, the very thing toward which our whole region was drifting, lay waiting in exactly that hidden lane. It is as though a traveler, asked which way the river of his whole world was flowing, found that the answer lay precisely behind the one mountain he could never see around, the mountain he himself was standing upon, and the Great Attractor, the hidden anchor toward which 500 million light-years of galaxies are falling, sits almost squarely behind it. The direction the flow points, toward Centaurus, toward the southern sky, lies low against the plane of the Milky Way, deep within the obscured band. The destination of the Great Fall was placed, by some accident of geometry, in precisely the one direction we are least able to see. The thing pulling us was hiding behind the very galaxy that the thing was pulling. We could measure the fall with great precision. We could draw the converging arrows. We could read the speed and the direction of the oldest light in the universe. And then we could turn our telescopes toward the place all of it pointed, and find our own galaxy standing in the way, a wall of dust and stars between us and the answer. Imagine the frustration of that. In the years after the flow was first mapped, you have discovered that an entire region of the universe, your own region, is falling towards something. You have measured the speed. You have fixed the direction. You know, beyond reasonable doubt, that there must be an enormous mass out there doing the pulling. And when you look, you cannot see it. Not because it is too far, though it is far. Not because it is too faint, though much of it may be faint. But because your own galaxy, the very thing being pulled, is standing directly between you and the source of the pull, its dust drawn across the destination like a hand held up before your eyes. The closer you look, the more the dust blocks you. The harder you stare, the less you see. For a time, this was simply the state of things. The Great Attractor was real, in the sense that its gravitational effect was real, measured, and undeniable. But it was also, in the most literal way, invisible. It was a mass without a face, a pull without a visible source, a destination without a picture. The astronomers had a name and a direction and a distance and a rough estimate of how much mass was required, and behind all of that, in the place the arrows pointed, there was only the gray blur of the galactic plane, the dust of the Milky Way drawn like a curtain across the most important region in our local sky. But astronomers are patient, and dust does not block every kind of light. Here, the story turns, because the very thing that made the Great Attractor invisible also held the key to seeing it. The dust of the galaxy blocks ordinary visible light. The light our eyes are built to see, the light our oldest telescopes were built to gather. Visible light has a short wavelength, and short wavelengths are easily scattered and absorbed by fine dust grains. That is why the dust is opaque to our eyes and to ordinary telescopes. But other kinds of light have longer wavelengths, and longer wavelengths slip through the dust more easily, the way a long ocean swell rolls past obstacles that would shatter a short, choppy wave. If you could build instruments that saw in those longer wavelengths, in the infrared, in the heat radiation that passes through dust as though it were not there, then perhaps you could see through the curtain. Perhaps you could look into the zone of avoidance and find what was hidden there. There was another window as well, at the opposite end of the spectrum. The hottest gas in the universe, the thin, searing gas that pools in the great clusters of galaxies, glows not in visible light, but in X-rays. This gas is heated to millions of degrees by the immense gravity of the clusters, and at those temperatures it shines in high-energy X-ray light that passes cleanly through the dust of our galaxy. So there were two ways through the curtain. Look in the infrared, in the long heat wavelengths that ignore the dust, and you could pick out the galaxies hidden behind it. Look in the X-rays, in the high-energy glow of the hottest gas, and you could pick out the great clusters of galaxies, the densest knots of mass, even where the dust of the Milky Way lay thickest in the foreground. So, the astronomers built the instruments and turned them toward the zone of avoidance, toward the blind spot, toward the place the Great Fall pointed. Surveys in the infrared began to map the galaxies hidden behind the dust, plotting their positions, counting their numbers, building a picture of the structure that had been concealed for so long. Surveys in the X-ray began to pick out the hot cores of galaxy clusters, the bright dense knots where mass piled up thickest. And as these new maps filled in, the curtain began, slowly, to grow transparent. The region behind the dust, the region toward which everything was falling, began to take shape, and what emerged was a structure. Behind the plane of the Milky Way, in the direction of Centaurus, there were galaxies, many galaxies, clusters of galaxies, a concentration of mass that had been there all along, waiting behind the dust to be found. At the heart of the region, the X-ray surveys revealed a great cluster of galaxies, a dense and massive concentration sitting almost exactly in the direction the flow pointed, almost exactly at the distance the measurements implied. Here, it seemed, was the source. Here was the anchor. Here was the visible face of the Great Attractor, finally pulled out of the dust and into view. A genuine concentration of galaxies, a real and massive structure sitting at the focus of the Great Fall, in the place the converging arrows had marked. After years of measuring a pole with no visible cause, the astronomers could finally look at the place the cause should be and see something there. The mystery, it appeared, was solved. The hidden mass had a location, a structure, a name. The fall had a floor, and for a while, that was the resting place of the story. The Great Attractor was no longer a pure abstraction, a gravitational ghost behind a curtain of dust. It was a region of real galaxies, real clusters, real mass, mapped in the infrared and the X-ray, sitting where it ought to sit, pulling as it ought to pull. The discovery felt like the closing of a circle. We had measured the fall. We had traced the direction. We had found our own galaxy on the way. We had built instruments that saw through the obstacle, and on the far side of the obstacle, we had found the thing. The mass that pulled us was a structure of galaxies in the constellation Centaurus, hidden in the zone of avoidance, now revealed. You could rest here, in the comfort of an answer found. The astronomers, for a time, did exactly that. But the universe is rarely so tidy, and the rest did not last. Because, when the astronomers added up the mass of the structure they had found, when they totaled all the galaxies, and all the hot gas, and all the clusters revealed behind the dust, and asked whether it was enough, whether this concentration of mass was great enough to produce the fall they had measured, the answer came back uncertain. The structure was real. The structure was massive. But the structure, by itself, did not seem to be quite enough. The mass they could see and count, in the place the arrows pointed, could account for much of the pull. It could not clearly account for all of it. There was a remainder. There was a part of the fall left over, unexplained, after every visible thing in the region had been weighed, and so the floor that had seemed so solid began, very gently, to give way. The Great Attractor was a real structure, yes, but the great structure, on its own, did not close the books. Some portion of the coordinated motion, some fraction of the long fall towards Centaurus, was not accounted for by the galaxies and clusters that had been revealed behind the dust. The pull was stronger than the visible mass could easily explain, and that left two uncomfortable possibilities. Either there was more mass in the region than the surveys had captured, mass too faint or too hidden even for the infrared and the X-ray to fully reveal, or the source of the extra pull lay somewhere else entirely, beyond the structure that had been found, deeper in the same direction, farther out along the same line. The astronomers looked deeper along the line, and when they looked past the Great Attractor, farther out in the same direction, far beyond the structure they had already found, they saw something that changed the scale of the entire picture. Hundreds of millions of light years beyond the Great Attractor, in the same general direction, sat a far larger concentration of galaxies. Not a single cluster, not a handful of clusters. A vast assembly of galaxy clusters, packed together more densely than almost anywhere else in the nearby universe, a concentration of mass on a scale that dwarfed the Great Attractor itself. It is called the Shapley supercluster, after the astronomer who first noticed an unusual crowding of galaxies in that part of the sky long before anyone understood what it meant. To grasp the scale of it, set aside the numbers for a moment and think instead in terms of crowding. Across most of the universe, galaxies and their clusters are spread thinly, separated by vast gulfs of nearly empty space, each cluster a lonely island in a great dark ocean. But in the direction of Shapley, the islands draw together. Cluster crowds against clusters, each one a city of galaxies in its own right, and the cities themselves gather into something larger still, a continent of clusters packed into a region far denser than the universal average. If the rest of the nearby cosmos is open water dotted with scattered islands, Shapley is the one place where the islands pile up into a crowded archipelago, a single great convergence of mass with few rivals anywhere within reach of our instruments. And all of that crowded weight lies along the same line as the Great Attractor, farther out, adding its distant pull to the nearer one, deepening the long incline down which our whole region slides. The Shapley supercluster is, as far as we can tell, the largest single concentration of mass in the nearby universe. It is a great metropolis of galaxy clusters, dozens of rich clusters drawn together into one immense structure. Each cluster itself containing hundreds or thousands of galaxies, the whole assembly bound and shaped by an amount of mass that is genuinely difficult to hold in the mind. And it lies in almost the same direction as the Great Attractor, farther out along the very same line that the Great Fall traces. So the picture rearranged itself again. The fall toward Centaurus was not, perhaps, a fall toward a single object after all. It was a fall down a long slope, a slope tilted by mass at more than one distance. The Great Attractor, the nearer structure, pulls us. And beyond it, deeper in the same direction, the immense weight of the Shapley supercluster pulls us as well, adding its more distant tug to the nearer one, both of them drawing us the same way down the same long incline. This was a more complete picture, and in some ways a more satisfying one. The Great Attractor was no longer a lonely anomaly, a single hidden mass that did not quite add up. It was the nearer feature of a deeper structure, the foreground rise on a landscape that climbed toward a far greater mountain beyond. The fall we measure is the sum of these pulls, the nearer one from the Great Attractor, the farther and even greater one from the vast Shapley concentration beyond it. Add the two together, the astronomers reasoned, and perhaps the books would finally balance. Perhaps the full 600 kilometers per second of our motion through the ancient light could be explained by the combined pull of the Great Attractor and, behind it, the colossal weight of Shapley. And this is largely where the careful, modern understanding now stands. Much of our motion, the long fall of the local group towards Centaurus, can be attributed to this combination, the nearer pull of the Great Attractor and the farther, larger pull of the Shapley supercluster beyond it, together with the broad tilt of mass across the whole region. the flow is real, the structures are real, and the largest part of the fall has a name, or rather two names, and a direction and a cause that can be pointed to in the sky. The story has a resolution that is honest and grounded and supported by decades of patient mapping. But, and here, the dark deepens again, the resolution is not perfectly complete. The accounting does not close to the last decimal. When the most careful measurements are weighed against the most careful inventories of mass, a quiet residue remains. Because the deeper astronomers have mapped these flows, the more they have found that the coordinated motion does not stop neatly at the edge of any one structure. The Great Attractor and Shapley account for much of it, but the flows seem to extend even farther, across even greater volumes, with contributions that are difficult to trace to any single visible source. Some studies find that a portion of the bulk motion comes from scales so large, from mass so spread out and so distant that it cannot be assigned to one cluster or even one supercluster. The fall is real, the major causes are known, and yet the full inventory of everything that pulls us, weighed against the full measurement of how we move, leaves a margin that is not yet completely filled. The visible structures supply most of the answer. They do not, with perfect confidence, supply all of it. And this brings us to the deepest layer of the matter, the layer that does not resolve into a tidy clump of galaxies behind the dust, the layer that touches one of the great unsolved questions of all of physics. Because the mass that does the pulling, the mass of the Great Attractor, the mass of Shapley, the mass of every great structure in the cosmos, is mostly not the mass we can see. The galaxies, the stars, the glowing gas, all the luminous matter we can map in visible light and infrared and X-ray, make up only a small fraction of the mass that actually shapes the motion of the universe. The great majority of the mass is dark. This is not the dust of the zone of avoidance, which merely blocks our view. This is something else, something stranger, woven through every galaxy and every cluster and every supercluster, exerting its gravity, bending the motion of everything around it, and yet giving off no light at all in any wavelength we have ever managed to detect. Astronomers call it dark matter, and the name, like the name of the Great Attractor, is a confession. It describes what the thing does not do. It does not shine. It does not block. It does not interact with light in any way we can catch. It simply has mass, and through that mass, gravity, and through that gravity, an immense and silent influence over the motion of every visible thing. We know dark matter is there for the same reason we knew the Great Attractor was there before we could see it. We know it by the way things move. Galaxies spin too fast for the visible mass within them to hold them together. They should fly apart, scattering their stars into the dark, and yet they hold, as though gripped by far more mass than we can see. Clusters of galaxies bend the light of more distant galaxies behind them, and the bending is far stronger than the visible mass could produce. Everywhere we look, on every scale, the motion of the visible universe implies the presence of much more mass than the visible universe contains. The luminous matter is the foam on top of a far deeper sea, and the sea is dark. So when we ask what the Great Fall is truly falling toward, the deepest answer is not the galaxies behind the dust, and not even the great crowd of clusters in Shapley beyond them. The deepest answer is the dark matter. The galaxies and clusters we can see are merely the bright markers of where the dark matter is densest, the lit windows of a far greater unseen structure. The Great Attractor is a place where dark matter pools thickly. Shapley is a place where it pools more thickly still. The visible galaxies trace the shape of the invisible mass the way scattered lights at night trace the shape of a city you cannot otherwise see. We are not falling toward the lights. We are falling toward the city, most of which never lights up at all. Hold the oddness of that for a moment. In the dark, the thing toward which everything falls is, in its overwhelming majority, a kind of matter that has never once announced itself to any eye or any instrument by its own light. It does not glow when it is hot. It does not glow when it is cold. It casts no shadow and reflects no beam. If you could somehow stand within the densest heart of the Great Attractor, surrounded on every side by the greatest concentration of its mass, you would see nothing unusual in the empty dark around you. No shimmer, no haze, no sign at all of the immense weight pressing in from every direction. You would feel only its gravity, the long, slow pull, and you would have to infer all the rest. This is the deepest strangeness of the whole story. The universe is built, in the main, out of a substance we cannot see, and the great structures that shape the motion of everything, the basins and the slopes and the hidden mountains of mass, are sculpted out of that unseen substance, lit only at their edges by the thin scattering of ordinary glowing matter that happens to have gathered there. We chart the dark by the light that clings to it, the way you might trace the outline of a sleeping figure beneath a blanket only by the few points where the cloth is drawn tight against the form beneath. And this is why the accounting is so hard to close, and why a residue of mystery still clings to the Great Fall even now. To weigh the Great Attractor, to weigh Shapley, to weigh the whole region toward which we fall, astronomers must somehow account for dark matter, the mass that gives no light. They infer it from the motion it causes, but that is precisely the thing they are trying to explain, and so there is always a danger of reasoning in a circle. They model it, they estimate it, they map its likely distribution from the visible galaxies that trace it, but the maps are imperfect, and the dark sea is deep, and there is always the possibility that it pools in places and amounts the models have not captured. The mass that pulls us is real, but a complete and confident inventory of that mass, totaled to the last unit, does not yet exist. The thing has a name. The name does not come with a full ledger. This is the honest shape of the matter. In the quiet hours, with no need to pretend the story closes more neatly than it does, we measured a fall, vast and coordinated, across 500 million light-years of space. We traced its direction to a hidden region behind the dust of our own galaxy. We found, behind that dust, a real structure of galaxies, the Great Attractor, and beyond it a far greater one, the Shapley supercluster. Together, with the broad slope of mass across the whole region, they explain most of the fall. And underlying all of it, mostly unseen, is the dark matter, the silent majority of the mass of the cosmos, the true shape of the thing we are falling toward, known only by the way it bends the motion of everything else. The major causes are mapped. The full inventory is not yet finished. There remains a margin, a residue, a quiet space in the books where the measured pole is slightly greater than the counted mass, and into that space the old wonder still flows. It is worth pausing in that quiet space to feel the strangeness of our position. We are inside the thing we are trying to measure. We cannot step outside the galaxy to look at it. We cannot step outside the flow to watch ourselves fall. Everything we know about the great motion we have had to learn from within it, by clever indirection, by reading the shift in ancient light, by measuring the speeds of distant galaxies and subtracting away the expansion, by building instruments that see through dust, by inferring the presence of mass we cannot see from the motion it causes. We are like swimmers in a vast, slow current with no shore in sight, who have nonetheless worked out, from the way the water moves around us and the way distant swimmers drift, that we are all being carried the same way, towards something none of us can see, somewhere far beyond the limit of our vision. That we have learned even this much from such a position is a quiet marvel, and the scale of what we have learned has a shape, and the shape has a name. When astronomers took all these flows, all the measured motions of all the galaxies across our region, and asked which galaxies share a common fall, which ones are sliding down the same great slope toward the same deep basin, they found that the answer outlined a structure far larger than any single supercluster as it had been understood before. They drew the boundary not by where the galaxies are, but by where they are going. Every galaxy whose motion leans inward toward the same great basin of attraction, toward the region of the Great Attractor, they group together into a single immense structure, and that structure is enormous. It contains the Milky Way and the entire local group, and the Virgo cluster, and many thousands upon thousands of galaxies spread across a region some 500 million light-years wide. They named this vast structure Laniakea, a word drawn from a language of the Pacific, meaning immense heaven or immeasurable sky. It is the supercluster that we belong to, defined not by a wall of galaxies, but by a watershed of motion, the great region of space within which everything flows toward the same deep gravitational valley. And the floor of that valley, the basin toward which all the flows of Laniakea drain, the lowest point of the great slope down which we are all sliding, is the region of the Great Attractor. We live on the long slope of an immense and invisible basin, and we are falling, slowly, across hundreds of millions of years toward its hidden floor. Picture it. In the dark, the way you might picture a vast landscape seen from above. Imagine the galaxies as droplets of water scattered across an enormous, gently sloping land. Each droplet, left to itself, rolls slowly downhill, drawn by the tilt of the ground toward the lowest point. The droplets near us roll the same way we do. The droplets farther off roll toward the same low place by their own slopes. And the whole landscape, the whole region of converging slopes, all the water that drains toward the same hidden valley, is Laniakea. We are one droplet among many thousands, far up on the slope, rolling slowly down toward a basin we cannot see, in company with everything around us, all of us drawn the same way by the tilt of space itself. But here, the landscape image, comforting as it is, must be handled with care, because the slope is not eternal and the valley may never be reached. The universe is expanding, and the expansion is not holding steady. It is accelerating. The space between distant galaxies is not merely growing, but growing faster and faster, driven by something even less understood than dark matter, a pressure built into empty space itself that astronomers, in yet another confession of ignorance, call dark energy. And this accelerating expansion works against the Great Fall. It stretches the space between the galaxies even as their gravity tries to draw them together. On the largest scales, the stretching is winning. So the slope we are rolling down is also, in a sense, flattening and pulling apart beneath us. The most distant parts of Laniakea are not bound to us by gravity strongly enough to overcome the expansion of space. They are being carried away faster than they can fall inward. The great basin toward which we lean may never gather its water at the bottom. The droplets may never reach the valley floor. The expansion may stretch the slope until the far droplets are carried beyond reach, drifting away into the growing dark while only the nearest, most tightly bound parts of the structure hold together and continue their fall. Laniakea, defined by its shared motion today, may not be a structure that endures. It may be a pattern caught in a single moment of cosmic time, already beginning to come apart, its outer reaches already being carried off by the swelling of space. This is the quiet paradox at the bottom of the whole story. We are falling towards something, with a direction, with a speed, with a measurable coordinated motion shared across 500 million light years. And at the very same time, the space we are falling through is stretching, accelerating, working to carry us apart. The fall is real, the pull is real, the pull is real. The Great Attractor is real, and Shapley beyond it, and the dark matter beneath all of it. But the destination may forever recede. We lean toward the basin, and the basin drifts away. We fall toward the valley, and the valley flattens beneath us. The motion is genuine, and the arrival is uncertain, and both of these things are true at once, held together in the long, slow dark of cosmic time. Let your mind rest for a while on the sheer indirection of how we know any of this. No one has ever seen the Great Attractor with their own eyes. No one has ever seen Laniakea as a whole. Never could, never will, for it is far too large for any single view, larger than light can cross in many human lifetimes laid end to end. No one has ever seen a single particle of dark matter. No one has ever stood outside the flow to watch the galaxies fall. Everything in the story has been read from indirect signs, from the faint warming of ancient light on one side of the sky, from the careful comparison of galaxy speeds, from the glow of hot gas in X-rays and the heat of hidden galaxies in the infrared, from the way light bends and the way galaxies spin and the way whole regions drift. We have built a picture of an immense, invisible, half-understood structure, and our place within it, almost entirely from the faintest of clues, gathered with enormous patience over many decades, by people most of whom never lived to see the picture complete. Think of how many separate lives that knowledge required. The one who first realized the spiral smudges were distant galaxies and not nearby clouds of gas. The ones who measured the recession of those galaxies and saw the expansion written plainly in their light. The ones who stumbled upon the ancient background radiation and slowly understood what they had found. The ones who built the instruments that read its faint warming and cooling, and so measured our motion through it. The ones who spent whole careers gathering galaxy speeds, one patient measurement at a time, until the flow emerged from the scatter. The ones who pierced the dust with infrared eyes and X-ray eyes, and drew the hidden structures out of the zone of avoidance. The ones who recognized that the visible mass was not enough and gave a name to the dark majority. The ones who took all of it together and drew, at last, the borders of Laniakea. No single mind holds all of this. No single life could. The picture we now carry was built by a long relay of human attention, handed forward across the generations, each contributor adding a little and then passing on, most of them gone before the next piece arrived. What you hold tonight is the gathered patience of all of them, distilled into a shape simple enough to fall asleep inside, and the picture is still not complete. That is the truth to carry down into sleep. And it is not a frightening truth, but a strangely peaceful one. We know that we are falling. We know roughly where. We know much of what the pulling is. And we know that some part of it, some quiet margin of mass and motion, is not yet fully accounted for. That the dark sea beneath the bright foam has depths we have not yet sounded. That the great fall carries us toward a place we have named but not fully measured and may never reach. The universe has not handed us a closed and finished answer. It has handed us a vast and partly open question, and the gift of having learned to ask it well. Think of how recent all of this is. For nearly the whole span of human existence, no one knew that the galaxies fell at all. No one knew there were other galaxies. The very idea that the faint smudges in the sky were island universes, vast and distant, is barely a century old. The discovery that the universe is expanding is younger than that. The mapping of the great flows, the naming of the Great Attractor, the recognition of Shapley's pole, the drawing of Laniakia's borders, all of it has happened within living memory, within a single human lifetime. The generation now passing remembers a time when none of this was known. We are the first people in the whole long history of our kind to know that we are falling, and where, and most of why. The knowledge is so new that the dust has not yet settled on it, so new that its own discoverers are only just beginning to grasp what it means. And you, lying here in the dark, are part of that. You are one of the first to know. You carry, in your understanding now, a map that no human being possessed for almost all of the time that human beings have existed. You know that the ground beneath you is falling, and the planet and the sun and the galaxy and the whole great crowd of galaxies that we belong to, all of it sliding slowly down an invisible slope toward an unseen basin in the direction of Centaurus, drawn by mass that mostly gives no light, across a region so large that the mind can hold it only as a kind of awe. You know this, and knowing it, you can let it carry you, the way the current carries the swimmer who has stopped fighting and begun, instead, to float. For there is nothing to do about the great fall. There is no resisting it, no steering, no need even to try. It asks nothing of us, it does not hurry. Across the whole span of a human life, of many human lives, of all of recorded history, laid end to end, the position of our galaxy on the great slope barely changes. The fall is so slow, by the measure of a life, that it is, for us, almost perfectly, a kind of stillness. It is the slowest possible motion, the most patient possible falling, a drift so vast and so unhurried that it feels exactly like rest. So let it feel like rest. Let the spinning of the earth, which you cannot feel, become part of the stillness of the room. Let the fall around the sun, which you cannot feel, become part of the quiet. Let the great sweep around the galaxy, 200 million years to the turn, become part of the slow background of the dark. And let the greatest fall of all, the long lean of our whole local universe toward the hidden basin behind the dust of Centaurus, become the deepest layer of that quiet. The floor beneath the floor, the motion so large and so slow that it wraps all the way around into stillness and holds you there. You do not have to understand all of it to rest inside it. You do not have to hold the numbers or the names or the distances. You only have to know the shape of the thing. Everything is moving together. Everything is leaning the same way, toward something we cannot see, across a distance we can barely imagine, drawn by a weight that is mostly hidden. In a fall so slow, it is indistinguishable from peace. That is the shape of it. That is all you need to carry down with you now. The galaxies are falling, and we are among them, and the falling is gentle, and there is nowhere we have to be, and nothing we have to do, and the whole vast invisible structure holds us as we drift. Out there, behind the dust, behind the curtain of our own galaxy's light, the hidden mass waits at the bottom of the long slope, patient, silent, unseen. And we lean toward it, all of us, all the galaxies of Laniakea together, in the immense slow motion that is too large to feel and too gentle to fear. There is no edge to fall off. There is no bottom to strike. There is only the long, slow, shared leaning of everything towards something we cannot see, and you within it, carried, held, falling so slowly that the falling is the same as being still. Let the rest of the night be that. Let the great fall be the thing that carries you down. Everything is falling towards something we cannot see, and so are you, and it is gentle, and it is slow, and it is the oldest and quietest motion there is, and it will go on carrying you long after the last of these words has faded into the dark. We are falling toward it. We have always been falling toward it. And tonight, for once, you can simply let yourself fall.